Next video, this is rational exponents. We're going to, in this video, distribute and factor expressions with involving expressions with exponents of the form m over n. So we're talking things like b to the m over n, stuff like that within expressions. We're going to factor and distribute with expressions having those types of terms. And the prerequisites for this, you need to know everything about exponents up to this point. That includes pretty much everything about rational exponents, everything about integer exponents, laws of exponents, all that stuff. Plus you need to know how to factor. Those are the two major prerequisites here. So let's get into some examples of what I mean. The first example we're going to start with is dealing with distribution. We have 2 times x to the 1/3, and we're multiplying it into this, well, it's not really binomial. I was going to call it a binomial, but we're going to multiply it into this algebraic expression, x to the 2/3 minus x. Now, something you should realize here is that it depends on what intermediate algebra course or what algebra course you're in. Some authors talk about this, some authors do not. But I think that any algebra textbook with worth its weight should talk about this topic. Distribution here acts like distribution anywhere. You take an object and you distribute it to each of the objects within that expression. So each of the terms there gets a 2x to the negative, or 2x to the 1/3 attached to it. So let's see what happens. This is going to be 2x to the 1/3 times x to the 2/3 minus 2x to the 1/3 times x. And that's, by the way, x to the first. All right, this first product here will have 2, and it'll be, we're just going to use law of exponents here to add these exponents. That'll be 1/3 plus 2/3. The second product will be 2 times, again, since these two bases are the same, I'm just going to add their exponents, 1/3 plus 1. Should be an expert at adding fractions at this point. This is 2 times x to the 3/3 or first. And this will be 2x to the 4/3 once you add those fractions. One last little step here. A lot of people don't like to have ones on their exponents. The 1 is already assumed, so it'll just be 2x minus 2x to the 4/3 power. That's it for that one. The idea of distribution is that you're essentially creating more terms than you originally had. Originally, we had, and maybe I should make this more apparent by erasing some of these markings. Originally, I had an object, this one right here, times another object, that one right there. So really, I only had one term there. Distribution creates more terms in general. So now I have 2 terms. Often distribution's not a wonderful thing to do. Usually we like to factor because it creates fewer operations. But it's still good to get this practice in on distribution. And the reason why I think most authors write in distribution first is so you can get used to the idea of distributing, and once you start factoring, it's pretty easy to realize, oh, factoring is just the opposite of distributing. So it's the anti-factoring, or the anti-distribution, sorry. So let's take a look at this next example. 1/3 z to the negative 1/2 times the quantity z to the 3/2 plus 2z to the negative 1/2. Again, I'm just being asked to distribute this, so I will. I'll take this monomial out front. It's not really a monomial. I really shouldn't say that. I'll take that expression out front and I'll distribute it to each of the terms here. And so when I do that, I'll write out the multiplication kind of slowly. I have 1/3 z to the negative 1/2 times z to the 3/2. It's a little messy the way I'm writing it, sorry about that. Plus, again, 1/3 z to the negative 1/2 times 2 z to the negative 1/2. All right, let's clean this up. In this first term here, I have 1/3, and that's it, so just 1/3. I'm not multiplying it by any numbers. And I have z to the negative 1/2 times z to the 3 halves, so I'll add their exponents, plus 1/3 times 2 is 2/3, z to the negative 1/2, plus another negative 1/2, right? You add their powers. Let's clean this up. That's 1/3 z to the, let's see, negative 1/2 plus 3 halves is 2 halves. So that'll be z to the first, plus 2/3 z to the negative 1/2 plus another negative 1/2 is a negative 1. Let me just write this one last time a little cleaner. 1/3 z plus 2/3 z to the negative first. And if you have an instructor that prefers your answers to be with positive exponents only, then you can write this as 1/3 times z plus 2 over 3z, right? Because you can rip the negative off that exponent and drop that z downstairs. Now we're going to try the opposite of distribution, which is basically factoring. Well, it's not basically, it is factoring. But I need to kind of convince you again, and I've done this in a previous video, but I think it's very important to see it again, that really all you're doing in factoring is that you're pulling out the most negative powered version of, or the least powered version of your variable. For example, if I told you to factor this, well, this is old school, you can easily factor this, and you ask yourself, what do these all have in common? And most people would say, oh, they have an x in common. You never really think about why you pull out the x. The reason why you factor out the x here is because, well, if you factored out x squared, this third term doesn't have enough power to be able to factor an x squared out of it. If I factor out an x cubed, on the other hand, well, the second and the third terms don't have enough power to factor out an x cubed. So that being said, I can factor out an x. Now, just to remind you what factoring is, it's dividing out a variable. So in other words, and normally you wouldn't have to do this, you do this kind of automatically in your brain. What we had there was a 3x cubed, and we're dividing off a power of x. So in reality, that would be a 3x, oops, I wrote a 2. It's a 3x squared. So that's what will go there, 3x squared. Plus, well, what was in this place was a 2x squared, but we're dividing off or factoring out an x, and so that's going to equal just a 2x. And finally, let's see, plus, in this last spot we had an x, and we're factoring off an x. Let me just keep everything the same. There we go. Factoring off an x is the same thing as dividing out an x. Well, x over x is equal to 1, so this is plus 1. By the way, when you reach the end of this, you should always ask yourself, is this the final answer, or can I factor this further? Well, you could try to factor 3x squared plus 2x plus 1, but you may find that it doesn't factor, because you need a 3x and an x and a 1 and a 1 plus and a plus, and if you did this, oh, that was supposed to be a plus. When you did this, you'll find out you get 3x squared plus 4x plus 1. So this actually does not factor. Okay? But that's how we normally factor polynomials. Well, the idea of factoring polynomials and factoring expressions is pretty much the same. You factor out common factors, or better yet, rule of thumb, and maybe I'll create a new page for this. When asked to factor, always pull out the lowest powered version of a variable. Now, I was going to say pull out the lowest powered version of all common variables. But the fact is, sometimes you will pull out a lowest powered version of a variable even if one of the terms doesn't have that variable. So maybe I'll have an example like that in this example set, but for now, the example that we're being asked to factor here, both of the terms have x's. So let's take a look at this. The lowest powered version of x here will be the 2/3 powered, right? Because the other one has a power of 1. So what's smaller, 2/3 or 1? Well, 2/3 is. So what I'll do is I'll factor out x to the 2/3. And I'll be left with something in its stead. Well, let's see. In that first place, we had 2x to the 2/3. but we're factoring out x to the 2/3. And it's pretty easy to see that those x to the 2/3 will cancel. They're the same picture. And they'll just become 2. So this will be 2 right there. Plus, well, in this spot, the term was x to the first. And we are factoring out x to the 2/3. Well, let me just convince you here. X to the first is the same thing as saying x to the 3/3. So if I have x to the 3/3 on top, x to the 2/3 on the bottom, who wins and by how much? The top wins. It has more power by 1/3. So that's x to the 1/3. Now, I use that language, who wins and by how much, but your instructor might say, listen, just do the law, one of the laws of exponents, which is take the top exponent and subtract off the bottom exponent. That's fine too. You get the same answer. But here we have it. So this is the factored version of 2x to the 2/3 plus x. It is going to be x to the 2/3 times the quantity 2 plus x to the 1/3. Now, honestly, this factorization is kind of trivial. There's not a lot that we gain by doing this. But it is an introduction to factoring. Honestly, the gains that we get in the long run for factoring far outweigh the trouble that we go through. It's just that in this problem specifically, we don't get any computational gains. But look at what we have here. This is exactly what I was telling you when I wrote down, let me pop down a couple, when I said when asked to factor, always pull out the lowest powered version of a variable instead of the common variable. Notice that each term here, that all three terms do not share a variable in common. So a lot of people would think you can't factor anything out of this. But in reality, I could write this to where they share a variable in common. This is 5d to the 1/3 minus 3d to the 0th plus d to the negative 2/3. Often I'll get students that ask me, well, am I supposed to do this from now on? Am I supposed to actually, write d to the 0th whenever I have a constant, a constant term? The answer is really no. This tactic is only really useful if you have negative exponents. Really only useful if you have negative exponents. That's really the only time you need to consider doing something like this. So if you do have an expression like this, and you're asked to factor, and you notice that one of your exponents on your variables is negative, then likely you can factor as long as you put a variable to the 0th power on the constant. Now when I look through each of these three terms that all have d in common now, I'm going to factor out the lowest powered version of that d, and that would be the negative 2/3. That's the lowest, the most to the left on the number line. So if I pull that out front, I have d to the negative 2/3 out front, and I'm left with some junk on the inside. Well, let's figure out what that junk is. In this first term slot, we had 5d to the 1/3, but I'm factoring out d to the negative 2/3. Now remember, I can rip that negative off that exponent and pop that d to the 2/3 upstairs. So that's what I'll do. I'll write this as 5d to the 1/3 times d to the 2/3. Because I ripped off the negative, it hops upstairs. And now I see that I have d to the 1/3 times d to the 2/3, so I can actually multiply those two. It's 5d to the 1/3 plus 2/3, which is just 1. So this is going to be 5d right here, to the first power. The next one, minus. I had 3d to the 0th, or basically 3. And I'm dividing out d to the negative 2/3. Again, rip the negative off that exponent and pop d to the 2/3 upstairs. So this will become 3d to the 0th plus 2/3, or in other words, 3d to the 2/3. Finally, plus, we had d in this spot right here. We had d to the negative 2/3, but I'm factoring out d to the negative 2/3. Well, you can easily see those are going to cancel, become 1, so this is just plus 1. there you have it. That's not so bad. I mean, we factored all that out. We do get some annoying exponents here, but still not so bad. Now, I didn't mention the last example, but you should check to see if this factors any further. Now, because this is not really a quadratic in here, but we have three terms, it really doesn't factor. So I'm just going to move on from this one and go into the next example. Now here comes the beast. This is the one that is going to take a little bit of thinking to factor. But just remember, when you're factoring, you're considering, first of all, how many terms there are. And I look at this, I see there's a term right here. I'll just highlight it really quickly. Here's a term, and here's the second term. So we have two terms. Each of those terms might have things in common. They might not. If I take a look at them, though, I know that they both can be divided by 3, so I'll pull a 3 out front. They both share x, so I'm going to write x. And remember, you're looking for the lowest powered version of that x, which will be the negative 1/3 right here. So I'm going to pull off x to the negative 1/3. And then I'm looking again because I see that they both share. Now this is where you have to use your little the skills of kind of pattern recognition, I guess you could say, where you kind of have to step back from the problem and notice that this picture, this picture right here, is the same as this picture right there. X squared plus 1 is the same as x squared plus 1. So you have to pay attention to that. And you say, oh, I noticed that both of those have an x squared plus 1 in common, so let me write x squared plus 1. And again, you want to factor out the lowest powered version of that, which is right here. It's negative 3/2. That's lower than negative 1/2. So I'll write negative 3/2 right here. And now you're going to be left with something. And I'll write this in braces like this, little brackets, I guess you could say. And here's where it's really important to do that whole business where I say what was here and I divide stuff out. It's very important that you do this. So what was there was a 3x to the negative 1/3 times x squared plus 1 raised to the negative 1/2. But what I'm doing is I'm dividing out, pulling out front basically, 3x to the negative 1/3 times x squared plus 1 raised to the negative 3/2. First things first, we can notice that the 3's will cancel nicely. 3 over 3 is just 1. And in fact, x to the negative 1/3 over x to the negative 1/3 will also turn into 1. So now I'm going to go ahead and rip the negative off this exponent in the denominator and pop that business upstairs. So this is just going to equal x squared plus 1 to the negative 1/2 times x squared plus 1 to the positive 3/2. Notice I didn't really knock that other one downstairs because they're the same base. I'm just going to add their exponents. It'll become x squared plus 1 to the negative 1/2 plus 3/2, or in other words, to the first power. Now that's really not a nice way to write that. X squared plus 1 to the first power is the same thing as saying x squared plus 1. So it was a little bit of work getting there, but it's so important for you to write out these divisions like this, because that's really what factoring is. It's just dividing out. So it really does help out when you do that so that you can get down the nitty-gritty with the problem and not make too many mistakes. Now I'll write plus here. In the second position, we had 6x to the 2/3 times x squared plus 1 raised to the negative 3/2. And what we're dividing off of that is 3x to the negative 1/3 times x squared plus 1 raised to the negative 3/2. Well, okay. I know that 3 will go in this 6 twice. And I know that x squared plus 1 to the negative 3/2 is the same thing as x squared plus 1 to the negative 3/2. So those two cancel out. So this, I'm going to rewrite just because it's a little bit messy, is 2x to the 2/3 over x to the negative 1/3. I'm I'm going to rip the negative off that exponent in the denominator and throw that business up top. So that's 2x to the 2/3 times x to the 1/3. Add the exponents. That'll be 2x to the 1, basically. So right here will be 2x. Now, something you should note here, and I'm going to erase this now because I don't need to reference it anymore. You can always rewind and watch what I did. This can be rewritten, so let me clean this up. 3x to the negative 1/3 times the quantity x squared plus 1 to the negative 3/2. And I'll reduce these regular old parentheses, and I'm going to write this in decreasing power order. So x squared plus 2x plus 1. Last thing you should do here is, after you're done doing a major factorization, which is what we did here, you should breathe a heavy sigh of relief, first of all. And then secondly, you should see if this trinomial factors. It actually does. It factors to x plus 1 times x plus 1. So that's going to be 3 times x. Well, you don't want to hear me say this out loud. I'll just rewrite it. Now, leaving it like this is pure laziness, so you should combine these two to be an x plus 1 quantity squared. And voila, we are done. If your instructor requires you to leave your answers with positive exponents only, well then go ahead and pop this stuff downstairs. That's okay with me. That'd be 3 times the quantity x plus 1 being squared, and everything with negative exponents here will pop downstairs, so you'll have x to the 1/3 and quantity x squared plus 1 to the 3/2. Okay, that's pretty much all I need to say about factoring and distribution with rational exponents. I mean, that's all the advanced factoring there is. Everything else from this point forward is just repetition. So you just need to be very aware. Always pull out the lowest powered version of your exponent or of your variable, and then do a slow division, like I have been doing in each of these problems. So for example, all this stuff right here, just make sure you do slow divisions like this so that you keep track of all your steps.